Next. Next. There you go.
Okay. This is the plot diagram. We have an input of a sine function, our transfer function in the middle, and our output is voltage in volts, and the input power is also in percent. The following parameters are important when we analyze a sine response curve. K is the gain. It's measured in volts per percentage. The order of the system, the ultimate frequency, which is in hertz. KCU is the ultimate gain in percentage per volt. Tau is the first order time constant, it's measured in seconds, and T naught is the dead time, also measured in seconds. This is the input and output voltage over time at a frequency of 0.4 hertz. It's moved some of it around. This should be right here. But you can get the period from the distance between two peaks after you've gone through the transient period. And then change of n is the distance from, it's just your, the top of your sine curve minus the bottom of your input. It's 10%. T naught is the difference between the top of your input and the top of your output voltage. And change in C is just the difference in the top of your output voltage and the bottom of your output voltage. And it was 12.2 volts. This was with it at 0.4 hertz. Our output voltage versus the input power, the frequency of 0.4 hertz. You can get change of M, just distance from the left and right side down here. And change in C is the top of the output minus the bottom of the output. Can also be measured there. Here's our Bode plot. I didn't have all the data available to me when I put this together for 69.5 to 70% input power. But for 70 to 80% input power, you can measure the gain as where this is, as the frequency approaches zero, it's the amplitude ratio, as the frequency approaches zero, we measured it at 1.8 volts per percent. The order, to get the order, I drew a line parallel to the end here, the last leg, and then put it at the bottom right of one of these units on the log function. And it looks a little different when I posted it. But it went up to, the rise was 0.8, it was 0.8 of the way up, and the run was 1 across to give us an order of 0.8. For the bottom half of our Bode plot, it measures the phase angle versus the frequency. You can see it looks relatively constant until, for the 0 to 69% input power in red, it looks relatively constant until it hits about here, and then it kind of trends downward, and the blue is kind of maybe to here and then trends downward. And that's for 70 to 80% input power. And you can also notice that and I'll mention this later as well, but if you notice the uncertainties on the left side, when the frequency is low, is a lot smaller than the uncertainties later. And that comes into play in a second. In order to measure the ultimate frequency, I had a point with a frequency here at 0.4 and 0.8 hertz, or I'm sorry, 4 and 8 hertz. And I used a logarithmic trend line to get an equation and solve for the equation here to get 7.05 hertz. For an ultimate frequency is when the phase angle is negative 180 degrees. KCU, or ultimate gain, is just the reciprocal of the amplitude ratio at that ultimate frequency. I did the same thing. I took that 7.05 hertz and I solved it for here I used a power trend line and was able to solve for the ultimate we were able to solve for the first order time constant using the following equation of point A, and that is the amplitude ratio is equal to k over the square root of 1 plus 2 pi f squared times tau squared, and we were just solving for tau there. We had all the other parameters. And then we were able to solve the dead time as well using the frequency, the equation for phase angle, which is negative 2 pi f t naught plus the inverse tan of negative 2 pi f tau. And those two equations we use there are also used to approximate the model amplitude ratio and the phase angle, which you see here. We've got the top here is the red is the model amplitude ratio over frequency with an input power of 70 to 80%. The blue is the actual amplitude ratio. And if you recall, the uncertainties in the beginning were very small, and then they got a lot larger. The frequency got larger, and so I chose to fit my curve to where the first few points with the lower frequencies matched up, since later it wasn't that experimental values weren't as certain. And then below that, and the purple is our model amplitude ratio for 0 to 69.5% input power, and the green is the actual amplitude ratio from 0 to 69.5% input power. And here at the bottom half, we have the phase angle versus the frequency again. What's important here is that when we model this curve, we change the parameters so that you end up, you want them close up here again, but then when you get to negative 180 degrees, you want the two to cross, which you can see that this would cross right about at negative 180 degrees, and so does this. And then we have all the means to be able to solve for the different key values for the model. For 0 to 69.5% input power, the gain is 0.1 volts per percent. The dead time is 0.60 seconds. The time factor is 0.93 seconds. The order is 1. The ultimate frequency is 4.5 hertz. And the ultimate gain is 0.22 percent per volt. And for 70 to 80% input power, the gain is 1.8 volts per percent. The dead time is 0.15 seconds. The time factor is 0.04 seconds. The order was 0.8. The ultimate frequency was 7.6 hertz. And the ultimate gain was 4.0% per volt. And to conclude, we have, I compared the step response and the sine response, the different parameters. This is our gain. In the blue is the step response values, and in the red is the sine response values. As you can see, for 0 to 69.5%, the step response and the sine response were very close to the gain. They were at about 0.15%, or 0.15 volts per percent. But for the 70 to 80% input power, it was a pretty dramatic difference. It went from about 5.6 volts per percent to about 1.8 volts per percent for the sine. Our dead times, they were dramatically different for 0 to 69.5% and 70 to 80%. We went from about 0.15 for the step response value for the dead time up to about 0.6 seconds for the sine response. And for 70 to 80%, we went from about 0.67 seconds down to about 0.4 seconds. And our time factors for the step response and sine response, again, it was a dramatic difference for the step response. For 0 to 69.5% input power, the time factor went from about 5.8 seconds down to about 0.9 seconds. And for an input power of 70 to 80%, the step response value time factor was about 3.1 seconds, and the sine response value for the time factor was about 0.5 seconds. Thank you for your time. Are there any questions?